The second offshoot of the lapply function is the vapply function. Again, I'm not sure where the v goes, but it has to do with values. It's probably tricky to read from a distance. I sort of switched around the words of that so that the v appeared first. Called it the value return is pre-specified apply. So what's going on here? What I've done is I've applied this 5num function, which gives you a 5-number summary of the of whatever input you have. And here, of course, in vapply, I've asked it to apply that on data vec1. Something tricky that it asks you to do is it wants you to label all of those rows in particular. And it also wants you to initialize a value. You see I've got an equals 0 there. If I had put equals 10,000 for each of those, it would have given me the same numbers. It just, for whatever reason, it needs you to initialize something. It gives you that structure so that you can print something, and again, so the values are returned in a pre-specified way in this particular lapply. This is the first time I'd ever heard of vapply. I was researching for this talk, so I'm not sure how often it's used, but it's there for you in case that's something that you care to use. So I thought that it was neat and I wanted to talk about it. Another version of apply that I want to talk about that's in the family is mapply. The M standing for multivariate in this case. And so what this does is it's essentially a multivariate version of apply. So it applies the function that you're after to the first argument of each one of these lists. For example, note that since it is a multivariate sapply, if you only put sort of a univariate, if you will, it'll spit out exactly the same thing as sapply would in this case. So that's not too bad, but we need to define something that will operate on each of these pieces. So what I did instead, in order to show the power of mapply, what we want to do is apply this over multiple ideas. So I went back to datamat in order to get sort of a multivariate data set. I considered each column of datamat. So datamat with a comma 1 inside the brackets, datamat comma 2, or comma 3 in this case, and datamat comma 5. So what I did in this case, I misstated a second ago, is I looked at the odd numbered columns in that matrix. So just to be clear about what exactly that was, there is datamat. So what I've asked it to do, that's our applied version of datamat. What I've asked it to do, I pulled out this column, and this column. So the first, third, and fifth columns. So that's what we're operating on. And I asked it to do a certain function that I defined in here. So this function was a little bit more complicated than x plus 1. So I put it inside of braces. And what this function is I ask it to look at the maximum of those three minus the minimum of those three. So remember what multivariate apply does, it goes to each element of those lists. So the maximum of A, B, and C in this case, you remember how I built datamat. So here the fifth column of datamat is always going to have bigger numbers than the third column of datamat, and which always has bigger numbers than the first column of datamat. So without too much trouble, you guys can recognize that the maximum is always going to appear in the fifth column of datamat, and the minimum is always going to appear in the first column of datamat. If you were to go back to datamat and match them up, because of this sequential way that I put them in, each element of, when you compare the first column and the fifth column going down those rows, every element is 24 bigger. Again, just to be super pedantic about that, I'll scroll back up to our matrix. And so what this is asking us to do is it's looking at 1, 13, and 25. It says, okay, what is the maximum number of those three? What's the minimum number of those three? And I want to take the difference. So the maximum, of course, is 25. The minimum is 1. 25 minus 1 is 24. And because of the sequential way that I built the matrix, you see we're comparing 2 and 26. 4 3 and 27, 4 and 28, 5 and 29, 6 and 30. So if we use mapply correctly, it should spit out 6 24s. And that is the output that it has produced for us. If we scroll down, there it is. All right. So that's a little bit about mapply. Now I want to talk about rapply. So the R stands for recursive here, and you'll even see it's defined as a recursive version of lapply. I must admit, I find that name not very intuitive. I don't think that it explains, that just calling it the recursive apply explains what it does, and moreover, it doesn't explain the power of what it does. So let's take a look at that. There's really two things that are really cool about rapply. The first one I want to point out, but the code that I have written here doesn't flex this particular muscle necessarily. There's a how argument that you can put into rapply, and what that does for us is it can return either listed or unlisted values. So you can sort of make it do lapply or sapply inside of it, depending on what you specify in the how function. The muscle that I chose to flex here is the class argument. So what that allows us to do is specify what kind of values we wish to apply the function over. So let's examine our friend datavec1 and compare that with datavec2 as it relates to rapply. Remember what the difference is between the two. Datavec1 has that third list as the numbers 21 through 30. datavec2 has that final list, that third list, as the letters A through J. If we look at, if we accept as an argument to lapply the vector datavec1, and then we also put it into rapply, it knows what to do if we ask it to square those numbers. Let's say the function that we write is x squared. It can square those numbers in both of those guys no matter what. However, if we were to use datavec2 in that same case and try to use lapply for it, lapply is not going to give us anything. It's going to throw up an error at us because it doesn't know how to square A. It doesn't know how to square B, these characters. So the magic of rapply is that we can tell it to only square integers, and it will go through that entire datavec2 and only square the integers, so it will actually give us something, and it will retain the letters A, B, C, all the way through J for that final list. So let's see how that looks. So again, the first thing that I did here was to show that lapply and rapply return the same thing for datavec1. Scroll up a little bit, and a little bit of inspection, you can see that these outputs are exactly the same. So why is that? Because we told it, I know that that's very, very hard to see from a distance. So we ask it to square integers, and we ask it to give it to us as a list. That says how equals, in quotes, list. So of course we could ask it to unlist that, and it would give us what would be if we had asked for sapply instead. So what is the magic of rapply? And that's sort of listed down here. So again, this is where my R markdown file and needing it to compile so I could present today is sort of less than intuitive. What I would rather it have done is just tell me what the errors are so that we show what that error is. So if we had run this piece of code, lapply for datavec2 with those letters, function x is x squared, there would be an error in x squared because there's a non-numeric argument there. We don't know how to square the character h, for instance. But if we run rapply and tell it that the class that we want it to work over is simply integers, it will actually render something. And you see what it does is it squares the integers that it finds, and it leaves all the non-integers alone. So again, I hope that you guys agree with me after that calling it the recursive apply doesn't really explain what exactly it does. So hopefully maybe there's somebody that worked on writing it can contact me and explain why it's called the recursive apply. I'd be interested to have an awesome explanation for it. I don't know what a better name for it would have been, but I certainly believe that the power is in this class argument that you can specify. And we are at the how equals replace. So replace and list, for whatever reason, give us the same thing. They will both give us this as a list. If we tell it how equals unlist, it will give this to us as sapply would have. So it's a little bit tricky, but so how sort of allows it to float back and forth between what kind of output it will give us. And replace and list mean the same thing for a how inside of rapply. So actually, when I wrote how equals list in quotes earlier, it's actually doing the same thing as how equals replace. So the last of the apply functions, I hope you guys can see now, there's a very large library here to work through. And the final of those that I will talk about today is tapply, T for table. So what the table apply does is it applies a function to each cell of what they call a ragged array. So what does that mean? In order to establish what this means, let's look at our iris data that's available in the base package of R. I talked about the iris data in my talk on support vector machines. I've attached it and printed out the top part of it. So of course, you guys of course know this already, but it allows us to see that the species is different for the flowers. So there's the first 50 flowers are setosa flowers, next 50 are versicolor, and then the final 50 are virginica. And so this is the very traditional tapply example in this case, is to ask it for the sepal length. So again, we've asked it to we've given it just the first column of this data matrix, and we have asked it to subset by species. So we want it to give us the average sepal length for each species, so it'll know to throw that in there over this ragged array, which essentially is just this table. It will search for all the setosa flowers, versicolor, and virginica flowers, and it will report the average of each of those sepal lengths to us. And so that is what this tapply function is doing for us. It's working over a table, or as they call it in the help pages, a ragged array. Are there any questions about any of the apply functions? Great, I'll hop back over to my presentation for a brief conclusion. So what have I talked about today? What am I hoping that you'll glean from my talk today? R is slow, but it's supposed to be slow. Because it's designed for you, it's not designed for the computer, but hey, we love it anyway because it was designed for us. We use it all the time. It's nice and simple. Get that line by line coding in there. It's very easy to pick it up for the first time. So there are many things that we love about it. It's not designed to be super fast. Another thing that we learned is that for loops are computationally cumbersome for R, and the reason for that is because R is an interpreted language and not a compiled language, so it's asking itself those questions every single time for every single entry down that loop. So especially in a big data setting, we're going to be staring at the computer forever waiting for some output. Because R is a functional programming language, and I introduced that term very, very briefly, function families like apply can work around all of these issues. So we'll let functions be the arguments of functions, and we can work around these problems in a much easier way. Of course, there are many, many types of apply functions. We just spent the last several minutes going through several of them. Which one we want to use depends on what kind of output we want and also what kind of data we're putting in. As you saw, there's generally a setup, but it changes for each apply function. So it's just reminding yourself what exactly each argument does, what arguments each function will accept. Finally, if you're interested in looking at this some more, of course, we talk about vectorizing code in R, and that's something that I chose to leave alone because I was running up against time for this lecture. Functions like subset, by, replicate, aggregate, all of those things some people would consider to be in the apply family. And the reason that I left those alone today is because they didn't actually say the word apply in them. It wasn't, apply or letter apply. So I just want to talk about those, but these guys certainly have some of the same power, some of the same capabilities. So I would encourage you to look at those as well. And finally, there's a package, the dplyr package, that is very flexible in terms of this applying. Apply as an apply. So it does all sorts of different things for all kinds of different data. So if you're interested in that, that is something that's also available. Thank you guys very much. Are there any questions?